So I've got the Nippon pulse motor in here with an incremental encoder connected to a Nano. The Nano is wired UVW, white, black, red. That's wrong. It should be red, white, black. But anyways, you got to phase it, and well, there's no Halls or commutation or no digital or analog Halls on this, so I got to wake and wiggle anyways. I got 48 volts connected for power. I got 24 for the V-Logic keep alive. I've got the serial adapter with the M for communicating, and I've got the encoder wired to the Hiroshi connector here. And if I had a shield, I could connect it to that tab there, but I'd also need to connect earth in here and make sure the heat plate at the bottom finds a path to earth. So let's take a look at the motor. So it's a tubular linear motor in here. It's a bunch of magnets stacked up. It's got a 60mm pitch for a pair of magnets. And then there's a moving coil. That's all integrated into this actuator here. But I had to try to find the motor. I couldn't find the part number for this linear actuator, but I found the 17 Newton meters of continuous force and the peak and all the constants, and that looks pretty good. So I believe this is the motor I have. Yeah, there's a bunch of drawings for it, and I saw the wiring. Yeah, red, white, black for UVW. So that's all the specky stuff on the motor. I'm using the Nano, which is the size of a postage stamp. This is the module. This is the module with the easy board on top. And this is the development board with the module plugged in. So I'm just going to use this without all the caps and the big connectors. You should have local bulk capacitance near a PWM switching amplifier, but my currents are low, so I'm not going to blow up the drive today. The last page of the data sheet shows you the connector kit for the easy board and all the bits and pieces, the Hiroshis. There's some wires in there with pins clipped on the end, so just cut them and poke, so easy to use. The serial adapter for using the CME software. And I installed the CME and I've got it connected. I'm using 8.2 CME with all the latest features. I got a Nano Plus. It's a PP for can open plus 90 volts, 10 amps, Z option. It's I got the latest firmware 5.3.4, but I think we're just doing a 4 branch 4.60. Anyways, I'm probably taking advantage of some feature for beta testing, so I got the latest firmware. That's fine. I'm just going to quickly run through the basic setup. It's brushless rotary. I don't have a brake. It's not vertical. It's hard to do algorithmic phasing vertically. It goes to the bottom and flops around like a fish, so maybe this is just a horizontal application. If you had Halls, I mean, I didn't see Halls on this, so maybe they could add digital Halls. I know they have analog sine cosine Halls, analog Halls for commutation and interpolation, but this has an incremental encoder. It's 0.5 microns, so 500 nanometer resolution. That's pretty good. This is the stop time if you want to cut the H-bridge for stow safety. Oh, yeah, that's the stow jumper right there. You got to plug that in to be able to enable your drive or connect it to your safety PLC or something. But you want to stop before you smash into the wall. Don't just cut the H-bridge and coast, right? Position, can, so that's good mode. Okay, it saves to flash. I didn't change anything. I entered the data for the motor, the model number, pitch, mass, peak continuous, torque constant, force constant, back EMF constant, inductance and resistance. So at 10 amps you'd need 35 volts, but I'm running on 48, so I still got volts left for speed, so that's pretty good back EMF, nice and low. For the current, I've got the current loop calculated values for the peak and continuous. These were calculated. I already tuned the current loop. I can't do the bandwidth button yet until this thing's phased. So let's take a look at that. I did the manual phasing, but I'll show you, like, you're not phased, right? Motor's not phased. You can't phase when you're disabled, so you got to enable it. Don't home. Don't move until you're phased. So it does a little wiggle thing. Now it's phased. Now you can move. Just a real quick on the manual phasing thing here. You can see you can put in a vector of current, and you can rotate it forward. Make sure the counts go up. Oh, that's nice. Good, good. And then it does this ramping up to some current values. I'm going to add increment 90 degrees, and if I'm banging in and out of a hard stop, and ignore the limit switches. And if I'm vertical and I want it to work with a brake, like not many linear motors have brakes, but they do exist, and so you hold and then you let go of the brake, and you hope it doesn't drop too far, so you do force phasing. And you can test the algorithm attempting to phase, and it's wiggling the motor, applying currents, and hey, now it's phased, so that's great. So I'm going to double check on the control panel, make sure I'm phased. Yes, I'm phased. Now I can do something like home. I'm going to home to a hard stop and apply some current. So here it comes to the negative end. Yeah, motor power wires, feedback connectors, little adapter to get to the easy board. But the homing is done, and you can save, you can home, you can save, and then you can exit. So I've already got it in flash here, so it's already tested. So now I can jog my motor because I home to 0, and I'm going to go in the positive direction. I'm just going to go to like 30 millimeters there, and I know what I was doing. I was testing some home soft limits. So after homing, the soft limits apply. So I can't smash into the hard stop even if I want to. It'll stop me before I get there, no matter how fast I'm going. So let's take a look at that. So yeah, it's already been tuned up. So I got the I did the the current loop tuning, then the velocity loop with auto setup checkbox, and then went right for position. You could do absolute moves because you're home, but I'm gonna move. So at 500 nanometers, that's 120,000 counts for 60 millimeters. So I'm going to try to smash into the hard stop, and I'm using an S-curve profile, so it'll ramp up nice and smooth, but it'll use the decel rate that's programmed in the homing screen here for deceleration. So that I can stop faster, but I want to see the effect of how does it stop me no matter how fast I'm going. So profile velocity following error. I guess I could look at current, actual current. That's always a good one. And I'm going to hit start. Bam, bam. There it goes. So it's going to repeat in reverse too. So you can see how it's starting to like S-curve, and then it hits a certain velocity, and it says I need to stop, so it decels like this is a trapezoidal stop. But then you can see like coming back, it's a nice S-curve move. So I'm just going back and forth in and out of the soft limit. Although the way it stops in the soft limit is not S-curve-ish. It's hard to calculate that on the fly. So you get more of a trap stop than an S-curve. Stop this again. Maybe I should. Yeah, let's not run into the hard stop. So we'll take a look at the S-curve without running it into the hard stop or too close to the hard stop and having it stop you at the soft limit. Pretty smooth. There's some error at the end there. I haven't tuned up too well, I suppose, but let's take a peek at the integral. There'll be some steady state error. There's a lot of drag with these cables here. I'm not using an IGUS chain or anything, so that might be some pull on it. But yeah, that settles nicely to within 10 counts of like steady state error. And then if we're integrating it, I don't know how fast we have to integrate to get there, but this will be a slightly faster integration. So we'll take a look at that. Yeah, that overdid it. So maybe ease up on the integration. So for tuning the velocity loop, there is a filter here. I moved the pole out on the V loop to 300 Hertz single pole, and that allowed me to get a little higher gains, but not too much bandwidth. The current loop's tuned up, should be about 1 kilohertz. Give it a little test here. 400 hertz. Okay, current loop bandwidth's a little bit low. I'm okay with that. If I was going faster and trying to settle faster and wanted more velocity loop bandwidth, maybe I should move that current loop pole out a little further. 2 poles together gets a little second order response, so that could be improved. This is a velocity limit for safety. You can't go this fast. If you do, you'll get a following error fault. There's some gains tuned by a human, nice round numbers. The math model's okay, but it's kind of soft and spongy. And then the proportional gain based on your mass, like does it bounce around, or should it be lowered if it's too big, or can you crank it up? Feed forward terms, those are always nice. Yeah, you can set your tracking window down, like I want to know when I'm within 10 counts for 3 milliseconds. I think that just about covers this. Maybe I'll talk a little bit more about some of the Nano web page features. So if we like the Nano, because it's small and powerful, you can see the drawings. There's a development board drawing. There's the reference design. Yeah, there's the reference design for the easy board. There's one for the development kit. You can copy our designs. It's the PCB files and the schematics, and you like this connector, you don't like that connector, change it, make it your own. There's a stow bypass jumper, and yeah, drawings. And the manuals, of course, there's like stow safety manuals. So it's got the safe torques. And then the firmwares, yeah, I don't see the plus firmware here, but that is the same as the AccelNet PCF plus common firmware. And so here's the regression tested. Oh, and here's Ethernet, EtherCAT firmware 4.88. So this 4.88 has Ethernet, Ethernet IP, TCP/IP, Modbus, all that stuff. This is, I guess, just the EtherCAT version, or you could, there's a CAN version. Yeah, look at that, production still shipping the 4.16, but I've been using the 4.60 for CAN Open. And again, new features, advanced features, like the encoder corrections. If you have a laser, you can do a correction table. Encoder corrections. This motor, I didn't see any cog in it, but there's also a cog comp too. But this is like, if you have a laser, you can measure the positions and then go back to them repeatedly. And this does have motor cog compensation in it too, but again, this motor doesn't cog, so I didn't see any cog. But yeah, there's different application notes here, so depending on what you're doing, you can find an answer to it. And let's see here. Oh yeah, feels smooth. Yeah, I think I'd have some sort of, I'm not sure if I like this dangling cable thing. Maybe an IGUS chain would be better. But that's it for the Nano with the Nippon Pulse tubular linear motor, all integrated into some sort of bearing package. Very nice. Thank you.